All right, folks, this video is the fourth and final one in a series of videos responding to your 3-2-1 survey on Chapter 5.4, Curve Sketching. You requested more examples of curve sketching with asymptotes, and so I've posted a worksheet with some examples of this, and today in this video, or in this series of videos, we will be focusing on one of those examples. So by the end of this video, you should be able to take all of the information that we learned in the previous three about f and its derivatives to sketch a graph of the function. So just to recap, what we've learned this week and what we've done in these videos is that to sketch a function, I want to use f to write down all the information I can about continuity, asymptotes, and intercepts. I want to use f prime to gather all the information I can about monotonicity, and f double prime to gather all the information I can about concavity. In this fourth and final step, and in this video, we will use all of this information, combine it, and sketch a graph. So the function that we've been looking at in these videos is x squared minus 4 over x squared minus 1. And in the first video, we determined that f had domain all real numbers, but excluding -1 and 1. F has intercepts -2, 0, 0, 4, and 2, 0. F had vertical asymptotes at x equals -1 and 1, and f had horizontal asymptotes at y equals 1. Now, you'll notice that I excluded the information here about whether it was approaching positive or negative infinity from the left or the right, and also whether or not this is approaching the asymptote 1 from below or from above. Now, I want to show you a neat trick that you can just use the derivative to find this information out. You don't actually have to compute any limits. In the second video, we determined where my function was increasing and where it was decreasing using the derivative. So it's decreasing on the intervals -∞ to -1 and 1 to 0. And it's increasing from 0 to 1 and 1 to infinity. This meant that f has a local minimum at 0, 4 because it switches from decreasing to increasing. Finally, in the third video, we found out what the concavity of our function was. We determined that from -∞ to -1, my function is concave down, concave up from -1 to 1, and finally concave down again from 1 to infinity. Notice f still has no inflection points even though it switches concavity because this happens at points not in the domain. So I have an inflection point only if I switch concavity at a place that my function's defined. Okay, and so we're going to graph this function now. And the way that we'll do this is we'll just start with a big coordinate axes. And the way that I typically begin is by trying to use the information that I found in these tables to draw vertical lines anywhere that I have an asymptote, anywhere that my derivative changes sign, or anywhere that my second derivative changes sign. So notice I have asymptotes at -1 and 1. My derivative changes sign at the critical value 0. And my concavity changes at -1 and 1. Those are already included by the asymptotes. So I'll draw vertical lines at -1. I already have one at 0. And I'll draw another vertical line at +1. So these don't have to be to scale. We're not going to worry about scale here. The only thing I would worry about is just make sure that this line is sort of as far away from that axis as the other. And so this is the line x equals -1. I'm choosing this because it's an asymptote. I also know that concavity switches here. This is the line x equals 1, and this is also an asymptote. And I'll also collect the information here that f prime is equal to 0 here at x equals 0. I'll also draw now a horizontal line anywhere I have a horizontal asymptote. So at y equals 1, I have a horizontal asymptote. I'm going to label this y equals 1. I'm going to write that I'm choosing this because it's an asymptote. And now maybe it would be good to find out, so here are my asymptotes, these dotted lines. Where am I approaching from? Am I coming from below with this horizontal asymptote or above? And how do I approach infinity or -∞? The point is actually, I don't actually need to compute these limits. I can use my increasing, decreasing table to do this, right? So my function, for example, decreases on the interval -∞ to -1, meaning I'm decreasing to this asymptote. So I must be going down. I'm decreasing again after that. I'm decreasing from the asymptote, which means I must be coming from +infinity. Here I'm increasing to the asymptote. I must be going up to +infinity. And here I'm increasing again from the asymptote, and so I must be going from negative infinity. As for the horizontal asymptote, I can use the same information. Negative infinity to -1, I'm decreasing, so I must be below, must be coming from below. And finally, on the last interval, I'm increasing, so I must be coming up below the horizontal asymptote. So that's all the information I got about asymptotes. Maybe I can also plot some of these points. 0, 4, again, this is not to scale. Let's say 0, 4 is around here. Let's say 2, 0, and -2, 0. So here will be -2, comma 0. And here will be 2, comma 0. And again, this doesn't have to be to scale, but try to make sure that things are at least proportional to each other to some extent. Next, so that's handled everything that I learned in the first step. Next, I'll look at my increasing, decreasing table to find out where my function is switching, it's increasing or decreasing. I've broken my plane up into 4 intervals. One from negative infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. And so I know on each of these intervals, my sign of my derivative is constant, my sign of the second derivative is constant, and so I know that it's either increasing or decreasing for this entire thing. I've broken it up into 4 intervals for which that's true. In particular, from negative infinity to -1, it's decreasing, the whole thing. From -1 to 0, it's also decreasing, so it's still decreasing here. Let's write this up here for room. Here it's now increasing from 0 to 1, so I'll write increasing. And finally, from 1 to infinity, it's also increasing. OK, so that's all the information I get from my second table. Also, I find out that this is a local minimum, so let's write the word min there. Finally, in the third video, we found out about concavity. Our concavity table tells us that from negative infinity to -1, my function's concave down, so I'll write CD for concave down. From -1 to 0, well, in fact, from -1 to 1, it's concave up, concave up. So CU, CU. And finally, on this last interval, I'm concave down again from 1 to infinity. So this is concave down. And that's it. There are no inflection points for us to plot. This is all the information from my tables. This is it. Now all I have to do is actually connect the dots, right? So I'm going to connect this asymptote with this asymptote through the point -2, 0, using a decreasing concave down curve. So decreasing means going from left to the right. I'm going down. Concave down means I'm curving down as well. And so that might look something like this, coming from this asymptote through the point -2, 0, and going down to this asymptote. So notice, I do this interval by interval by interval. From this asymptote, I come down, and I go to the point 0, 4. I'm decreasing and concave up, meaning I'm going down from left to right, and I'm curving up. So that might look something like this. It's OK if yours doesn't look exactly like mine. They're going to look different. Now, on this interval, I'm concave up and increasing. I go from the point 0, 4 to the asymptote. Looks something like this. And finally, on this last interval, I'm concave down and increasing, which means I'm coming from this asymptote, going up from left to right, and curving down. And so I have to connect these two asymptotes through the point 2, 0. OK, and that's not bad. If you look at a graph of this function on an algebra calculator or on your calculator at home, you might find that it's scaled a little bit differently, but the general picture should be very much the same. And so what we've done, we've used all the information that we have about concave down, or concave up, and monotonicity. We've written all of that here just as a guideline. We've written down all the information we know about asymptotes. We've written down everything we know about special points that we found, and then we just connected the dots. At the point where I'm actually graphing, I'm not looking at tables anymore because I've already translated my tables into the graph. And that's what makes this much easier to do than actually trying to do the whole thing at once. So I hope you got something out of these videos, and I'll see you on Monday.